Hello everyone, welcome to my presentation. My name is Akash Patel. Today I will be explain understanding confusion matrix and classification error, which is one of the most important topic in machine learning model evaluation. When we build a machine learning model, our goal is to make accurate predictions. However, simply building to the model is not enough. We also need to understand how well it performs and whether we can trust its predictions in real world situations. Many beginners judge a model only by its accuracy. Although accuracy is an important metric, it does not always tell us the complete story. A model can still make important mistakes even when its accurate looks very high. In the in this presentation, we will learn why that happened, how a confusion matrix helps us evaluate a classification model, and what different predictions outcomes such as true positive, true negative, false positive, and false negative actually mean. I will explain each concept step by step using the simple language and practical examples so that even if you are new to the machine learning, you can easily understand the topics. So let's get started. So before learning about confusion matrix, let's first understand why evaluating a machine learning model is so important. So training a machine learning model is only the first step. After the model learns from the training data, we need to evaluate its prediction to see how well it performs on new data. This evaluation help us decide whether the model is reliable enough to be used in real applications. Classification models are used in many areas such as fraud detection, spam email filtering, disease diagnosis, and image recognitions. In each of these applications, the model predicts a category, but those predictions are not always correct. Many people only focus on the total number of correct predictions, while this gives us an overall idea of performance. It does not explain whether the model is making mistakes. So let's take a simple example. Imagine a bank process 1,000 transactions in a day and only 10 of them are actual fraudulent. If a model predicts every transactions as not fraud, it will correctly classify 990 transactions and achieve 99 accuracy. Even though the accuracy looks excellent, the model completely missed all 10 fraud cases, uh, which are actually the most important transactions to identify. These examples shows why accuracy alone cannot fully describe a model performance. We also need to know which predictions were correct, which was incorrect, and type of mistakes the model made. This is exactly why model evaluation is so valuable. It helps us understand the strengths and weaknesses of a model and give us the information needed to improve it before using it at the real world systems. Now that we know why evaluation is important, let's look at two basics value that every evaluation process begin with. Let's move to the next slides. So before we can understand a confusion matrix, we first need to understand two basics terms: actual results and predicted result. The actual result is the correct answer that already exist in the database. It represent what really happen in the real world. The predicted result is the answer generated by the machine learning model after it analyzed the available information. So the purpose of model evaluation is to compare these two values. So if the predicted result matches the actual results and the model has made a correct predictions. If the two values are different, the model has made a incorrect predictions. So let's understand this with a simple fraud detection example. Suppose a bank transaction is actually fraudulent. If the model predicts fraud, then the prediction is correct because the model successfully identified the fraud. Now imagine the same transaction is actually fraudulent, but the model predict not fraud. In this case, the model has failed to recognize the fraud, so the prediction is incorrect. The opposite situation can also happen. Transactions may actually be normal, but the model predictions fraud even though the model is trying to detect suspicious activity. It has incorrectly classified a legitimate transactions. Every predictions made by a classification model can be evaluated by com- comparing these actual and predicted values. This simple comparison become the foundation for the confusion matrix and every performance matrix that we will learn later in this presentation. In the next slide, we will see why relying on only on accuracy can something create a misleading picture of the model performance. So now that we understand the difference between actual and predicted results, let's look at this why accuracy alone is not always enough to evaluate a machine learning model. Accuracy simply measures how many predictions the model made correctly out of the all predictions it made. For example, if a model made 1000 predictions and correctly predicts 950 of them, then the model has 95% accuracy. At the first, this sounds like an excellent results. However, accuracy only tells us how many predictions were correct overall. It does not explain which predictions were correct or what kind of mistakes the model made. Let's use the fraud detection example again. Imagine a bank used 1000 transactions where 990 are normal and the only 10 are actual fraudulent. Now suppose the model predicts every transaction as not fraud. Since most transactions are normal, the model correct predictions 990 transactions and achieve 99% accuracy. But there is only one major problem. The model completely misses all 10 fraudulent transactions, which is actually the most important job of the system. So even though the accuracy looks excellent, the model is not useful because it fails to detect any fraud. This is a common problem when one class appears much more often than other. Accuracy alone cannot solve these important mistakes. That is why machine learning engineers use better evaluation methods such as the confusion matrix to understand exactly where the model performs well and where it needs improvement. In the next slides, we will see how a confusion matrix help organization. All of these predictions result in a much clearly way. So now that we know why accuracy can something sometimes be misleading, let's learn about one of the most powerful, useful tools for evaluating a classification model, which is the confusion matrix. A confusion matrix is a table that compares the actual results with the predicted results made by the machine learning model. So instead of giving us only one number, such as accuracy, the confusion matrix separates every predictions into different categories. This allows us to clearly see how many predictions were correct and what kind of mistakes the model made. For a binary classification model problem, where there are only two possible classes, such as fraud and not fraud, every predictions belong to one of four possible outcomes. These outcomes are true, positive, true, negative, false positive, and false negative. Each outcome tells us something different about the model performance. Some represent correct predictions, while other represents mistakes that may have different consequences depending on the application. This detailed information help us understand the model much better than accuracy alone. It also becomes the foundation for several important evaluation metrics, including precision, recall, specific, specificity, and F1 scores. which we will learn in the following videos. So before learning these four outcomes, we first need to understand what the word true, false, positive, and negative actually means. So before we study the four predictions outcome, it important to understand the meaning of the word true, false, positive, and negative because they appear throughout the confusion matrix. Let's start with the first two terms. True simply means that the model prediction is correct. It false means model prediction is incorrect. Now let's look at positive and negative. These words do not automatically mean something is good or bad. Instead, they are simply label used to represent the two classes in the classification problem. For example, in the fraud detection system, we usually consider fraud as the positive class, while not fraud become the negative class. In the medical diagnosis system, the positive class might represent disease, while the negative class represents no disease. So the meaning of positive and negative depends entirely on the problem we are trying to solve. A very easy way to understand every predictions is the task. Ask yourself two simple questions. First, what did the model predict? Second, was the predictions correct? The answers of to these questions allow us to identify whether a prediction is true positive, true negative, false positive, or false negative. Now that we understand these basic terms, we are ready to learn each of the four outcomes one by one, starting with true positive, true negative. So now that we understand the meaning of true, false, positive, and negative, let's look at the first two outcome in a confusion matrix, true positive, true negative. Let's begin with the true positive, also called TP. A true positive happens when the actual result is positive and the model correct prediction is as positive. In simple words, the model correctly identify a positive case. For example, imagine a bank transaction actually fraudulent. If the machine learning predicts fraud, then it has made the correct decision. This is called the true positive because the fraud was successfully detected. Now let's look at true negative OTN. The true negative happens when the actual result is negative and the model correctly predicts it as negative. Using the same example, suppose the transaction is actually normal. If the model predicts not fraud, then it has correctly recognized a legitimate transactions. This is called a true negative. Both the true positive and true negative represent correct predictions. The difference is simply the type of case they correctly identify. One correctly detects positive case while the other correctly recognizes negative cases. A reliable machine learning model should perform well in both situations because correctly identifying both positive and negative cases help improve the overall performance of the system. Now we have learned the correct predictions outcomes. Let's move on to the two types of predictions error. So the next two outcomes are false positive and false negative. These are very important because they represent the mistakes made by a machine learning model. Let's begin with the false positive or FP. The false positive happen when the actual result is negative, but the model incorrectly predicts it as positive. In our fraud detection example, imagine a transaction is actually normal, but the model predicts fraud. The system incorrectly treat a legitimate transactions as suspicious. This is called as false positive, and it often referred to as the false alarm. False positive can create unnecessary work for employee, inconvenience customers, and sometimes even block legitimate transactions until they are reviewed. So now let's look at false negative. And false negative happen when the actual results is positive, but the model incorrectly predicts as it as negative. For example, suppose a transaction is actually fraudulent, but the model predicts not fraud. In these situations, the fraud goes undetected because the model failed to recognize it. This type of mistake can be much more serious because it may lead to financial losses or security risks. Although both false positive and false negative are predictions errors, these impacts can be very different depending on the applications. In some system, reducing false alarm is more important, while in the other, detecting every positive case become the highest priority. Understanding these differences help us evaluate a model more effectively instead of simply counting the total number of mistakes. Now that we have learned all four outcomes uh, individually, let's see how they work together in a confusion matrix. Let's move the next slide. So at this point, we have learned the four possible outcomes of the classification model: true positive, true negative, false positive, and false negative. Now let's connect them together and understand how they describe where predictions made by the model. Whenever the model makes a predictions, only one of these four outcomes can occur. If the model correctly identifies a positive case, it is a true positive. It correctly identifies a negative case, it's it is a true negative. It's incorrectly labeled a negative case as positive, it become a false positive, and it fails to identify a real positive case and predict it's a negative, it become a false negative. Together, these four outcomes give us complete picture of the model performance instead of simply knowing how many predictions were correct. We know understand what kind of predictions were correct and what kind of mistakes the model made. This information is much more useful than accuracy alone because different mistakes can have different consequences. For example, fraud detection systems missing a real fraud case can be much more serious than creating a false fraud alert. In other applications, the opposite might be true. This is why machine learning engineers always look at these four outcomes before deciding whether a model performed well enough for a particular task. So now that we understand the four outcomes of the confusion matrix, let's apply them to the real example and see what they tell us about a machine learning model. So imagine a fraud detection model has been tested using 350 bank transactions. After comparing the model's predictions with the actual result, we get four different outcomes. The model correctly identified five fraudulent transactions. These are called true positive because the transactions were actually fraudulent. The model successfully detect them. Next, the model incorrectly labeled 20 normal transactions as fraud. These are false positive because the model create fraud alert for transactions that are actually legitimate. The model also misses 10 fraudulent transactions by predicting them as uh, not fraud. These are false negative because real fraud were not detected. Finally, the model correctly identified 100 normal transactions as not fraud. These are true negative, showing that the model correctly recognized legitimate transactions. This example shows why the confusion matrix is much more useful than looking at accuracy alone. Instead of giving us only one number, it helps understand exactly where the model performed well and where it still need improvement. So now every predictions error has the same impact depend on the applications. One type of mistakes may be much more serious than other. Let's continue with our fraud detection problem. Example: false positive happens when the normal transaction incorrectly flagged as fraud. Although this can be inconvenience for customers or may require additional investigation, the transaction can usually be reviewed and approved later. A false negative, however, is often much more serious in the situation fraudulent transaction is predicted as normal, allowing the fraud to go undetected. This can lead to a financial loss or security risk for both the customer and the bank. The idea applies to many other machine learning applications as well. For example, the medical diagnosis system missing a serious disease could delay treatment and affect patient's health. On the other hand, a false alarm may simply require additional medical test to confirm the diagnosis because every application has different priority. Machine learning engineers cannot evaluate every model in exactly the same way. So instead, they choose evaluation metrics based on the type of mistakes they are most important to reduce. This is one of the main reasons why understanding the confusion matrix is so valuable. It helps us identify not only how many mistakes the model makes, but also which mistakes are the most important. Let's look at a few more real-world examples to see the idea applies to different machine learning systems. So although we have been using the fraud detection throughout this presentation, the same confusion matrix concept apply to many other machine learning applications. Let's look at few examples. In a spam email filter, a false positive happens when an important email is incorrectly placed in the spam folder. As a result, the user may miss an important message. A false negative happens when a email is incorrectly delivered to the inbox instead of being filtered out. Now considered a medical diagnosis systems. A false positive may indicate that a healthy patient is suspected of having a disease. This could lead to additional medical tests, but the doctor can usually confirm the final diagnosis. A false negative is often much more serious because a patient who actually has the disease may not receive treatment on time. Another example is security monitoring systems. A false positive create unnecessary security alert that waste time and resources. Time example shows that the same confusion metrics can be used in a different fields. As machine learning engineers, our goal is not only to build accurate model but also to understand which predictions error matter the most and select evaluation method that match the need of the applications. Now we understand the confusion matrix and different classification errors. We are ready to learn how these four outcomes are used to calculate important evaluation metrics such as precision, recall, specificity, and F1 scores, which will be focused on our next presentation. So far, we have focused on a binary classification where the model predict only two possible classes such as fraud and not fraud. However, not every machine learning problem has only two classes. Many real world applications require the model to choose more multiple categories. This type of problem is called a multi-class classification. For example, the image classification model might identify whether an image contains a cat, dog, bird, or a horse. Similarly, a customer classifications systems might group customers into low risk, medium risk, and high risk category. In these situations, a confusion matrix still works the same way, but instead of having only two classes each, it includes all possible classes. This allows us to see which category are being predicted correctly and which category are being confused with another. To make this information easier to understand, many machine learning tools display that confusion matrix as a heat map. A heat map uses different color uh, intensity to represent the value instead inside the confusion matrix. Calls cells with large value usually appear darker, making it much easier to identify patterns and common predictions errors. Instead of reading every number individually, we can quickly recognize where the model performs well and where it frequently makes mistakes. Whether we use a table or a heat map, the goal remains the same: to better understand the model's behavior and identify areas where it can be improved. Now that we understand how confusion metrics work for both binary and multi-class problems, let's see how they lead to even more powerful evaluation metrics. Although this presentation we have learned that confusion metrics provide much more information than accuracy alone. Instead of giving us only an overall score, it separates every predictions into true positive, true negative, false positive, and false negative. So, however, the confusion matrix is only the starting point of the model evaluation. Machine learning engineers often need to answer more specific questions. How many actual positive cases did the model successfully detect? How well does the model recognize negative cases? How can we balance different types of predictions error? To answer these questions, we use additional evaluation metrics that are calculated directly from the confusion matrix. So, some of the most important metrics are recall, precision, specificity, and F1 scores. Each one focus on a different aspects of model performance and help us evaluate the model from different perspective. So, in our next video, we will learn precision, recall, F1 score, and specificity explained. Let's move to the next slide. So this brings us to the end of today's presentation. Today we learned why evaluating a machine learning uh, model is just as building one. We also discovered the accuracy alone cannot always describe how well a classification model performs. We explored the confusion matrix and learned how every prediction falls into one of four outcomes: true positive, true negative, false positive, or false negative. Finally, we looked at how confusion metrics can also be used in multi-class classification and how they provide the foundation and for more advanced evaluation metrics. So thank you so much for taking the time to watch presentation. I hope you found it helpful and easy to follow. In my next video, I will explain precision, recall, specificity, and F1 score, and so how these metrics help us evaluating machine learning models even more effectively. So, also special thanks to my professor. I would like to sincerely thanks Professor Dr. Swami for his continuous guidance, encouragement, and support throughout my learning journey. His practical teaching approach and commitment to student success continue to help me better understand machine learning, cloud computing, and real world AWS technologies. So that's it. Thank you so much and have a wonderful day.